When discussing creation evolution, there's a lot of issues to talk about. Some of the issues are including biblical authority, which Chris talked about this morning. Other issues are building a creation model from the Bible, and that's an important area of study. Another area is removing stumbling blocks from people in believing creation in the first place, and that's the category that this morning's talk here will fall into. This is an important topic to me personally because it was this question actually that led me on the journey to accepting creation and accepting the Lord as a Christian. I was an atheist until I was 27 years old, and I was working in the military space program at the time when a Christian coworker, we started talking about origins, and he challenged me on my beliefs in atheism and deep time evolution and so on. And the first question he asked me was, "You believe in the laws of physics, don't you?" And I said, "Well, yes, of course, we use them here every day." He said, "How do you reconcile them with the Big Bang?" And he didn't even explain what he meant, actually. And he didn't actually have to, because it was like a little switch clicked in the back of my brain somewhere, and I realized that those two things didn't match. Physics over here, Big Bang model over there. So that got my attention enough to then begin a much longer process. And it took the better part of a year for me to abandon my atheism and turn to my current position, which is biblical Christianity. And I mention that to make the point, a lot of times we're told by the opposite side in this debate that we're only creationists because the Bible forces us to be. That because we have faith in this book, the Bible, which requires creation, therefore we believe it. And that if we weren't blinded by our faith in the Bible, we would certainly see all this evidence for evolution if we could just look at science objectively without the blinders that our faith puts on us. And I mentioned my own personal story here at the beginning to make the point. I went through all the evidence I could find in all the various sciences, not just astronomy, before abandoning my atheism and then accepting that the creation account was true. I became a Christian after that point. So I'm one among many who are not creationists because we're Christians. The creationism came first. I became a creationist before becoming a Christian. Now, becoming a creationist is not sufficient to make you a Christian. That's the work of the Holy Spirit. I mean, there are Muslims who are creationists. But again, I'm making the point that this is not an issue that we're blindly accepting something because the Bible requires us to. There's good scientific evidence for our side and good scientific evidence against the other side, and that's the theme here this morning. Now, when dealing with the universe, the question is, where did all this come from? And there's two primary interpretations here. It's not all that complicated. Either it was created or it wasn't. If it was created, then that, of course, invokes the biblical account where in the beginning God created the heavens and the earth. But we're told that this explanation is invalid. It's not allowed. Why is that? Well, because it's supernatural. The prefix super just means above or beyond. So supernatural means above or beyond nature. And we're told that naturalism is the only allowable scientific viewpoint. That we're only allowed to invoke natural processes to explain the natural world. And that anything supernatural, then, by definition, is not science, and therefore unallowable. Now, the primary naturalistic viewpoint for the origin of the universe today is the Big Bang model. And we'll discuss in a little more detail what this is here. It's hard to summarize such a thing into one graphic. Here's an attempt that NASA took at it. You can see at the beginning was what they refer to as a quantum fluctuation, where something happened. That something then turned into the universe, which then expanded rapidly in a period called inflation. And again, we'll talk more about each of these steps. Rapidly ballooned outward. At the beginning, you had this, which gradually turned into stars and galaxies and so on, and here we are to talk about it. Now, our time here this morning will be spent discussing three primary subjects, or three primary approaches. First, I'm going to show why it is claimed that the Big Bang is good science. I'm going to show you the primary lines of evidence that are viewed as support for the Big Bang model, indeed, that require the Big Bang to be true. Then we're going to dig a little deeper and find out actually the Big Bang isn't good science, it's really bad science. Because there's a lot of scientific evidence against the Big Bang model that, in my opinion, and the opinion of many others, outweighs whatever positives it may have. And then I'm going to go one step further. I'm going to say that the Big Bang is not good science. It's not even bad science. It's actually anti-science. The Big Bang, when taken to its logical conclusion, makes science itself impossible. Now, that's a pretty bold statement, wouldn't you say? So, we better get started. We'll start with good science. Before we can discuss why the Big Bang is considered to be good science, we have to, of course, decide what the Big Bang is. I'm showing you here a photograph of the universe, with the exception of this, which is a star, and this star here, and that one, and a handful of others. Every other dot, speck, blob, point of light you see in this photograph is a galaxy. Galaxy, on average, contains 100 billion stars. So you're looking at thousands of galaxies here, and you can imagine all the stars that are represented. This view of the sky, this entire photograph, is the amount of sky that would be blocked from your view if you held a grain of sand above your head at arm's length. So the cosmos is incredibly vast, beyond our comprehension, really. I mean, we can assign numbers to it, but you can't really understand what's going on. So where did all this come from? Well, what we're being told is this, that in the beginning there was nothing, and there was a fluctuation of that nothing which turned into something. The something blew up, basically, formed a bunch of energy, which formed into gas, which formed into matter, which then formed stars, which then formed into galaxies, and eventually there was planets along the way as well. And here we are to talk about it. Where did such an idea come from? Well, a lot of it comes from the work of a man named Edwin Hubble. Hubble was an interesting character in his own right for various reasons, but he was a pioneer in studying the redshift of distant objects. What is redshift? Well, if you see on this, what appears to be a rainbow kind of color here, this is sunlight that has been run through a spectroscope. And a spectroscope is something that breaks light up into various wavelengths. A crude spectroscope, for example, is a prism. If you've ever run sunlight through a prism, you notice that a bunch of colors come out the other side because the white light going in is then broken up into its various colors coming out. Now, if you have a good enough spectroscope, you can see that sunlight actually is not a continuous pattern of colors. You see that there's these vertical lines in here where there's colors missing. Turns out that when light passes through a gas, for certain reasons, the gas absorbs specific wavelengths of the light. So those colors are then subtracted from the rainbow spectrum that you would otherwise get. And by doing this, we can measure to see what gases are in the atmosphere of a star. For example, like I said, this is sunlight, so we can look at the pattern of lines that are produced and figure out what elements are in the atmosphere of that star. Interesting trivia point, the element helium was actually discovered on the sun before it was discovered here on Earth. They broke sunlight up and accounted for most of the lines, but there was a few left over in a new pattern. They said, well, this must represent some element that we're not familiar with. Thus its name, helium. It's named after Helios, the Greek sun god. So why are we getting into this? Well, because we have the sun as a reference point. I mean, the sun is a stable distance from the Earth. The Earth's orbit isn't perfectly circular, but we can compensate for that. When we look at faraway objects, though, and measure their light, it's a little bit different. Notice how there's a similar pattern of what are called absorption lines, but they're shifted as a group over in this direction, toward the red. As you might guess by the name, it's called redshift. What's going on here is that the light is effectively being stretched. Now, Hubble was among those who discussed the fact that we see redshift basically everywhere we look in the sky. There are a few objects that are blue shifted, meaning the light is being compressed in a sense, which means those objects are moving toward us, but everything else is red shifted. What does that mean? I apparently have a slide that's missing here because it illustrated that the stretching of light to form the redshift is an indication that that object is moving away from us. So since all objects at non-local distances are redshift, or at least their light is, Hubble thought, well, let's investigate this a bit further, and he correlated a lot of this data and realized that if everything is moving away from us, well, imagine taking a movie of the universe as all these objects move away from us. Run the movie backwards, and you see that everything gets closer and closer together until eventually everything would be at the same place. And this is the fundamental idea of the Big Bang model. If everything, with only a few exceptions locally, if everything else is moving away from us as time progresses, then looking backwards in time, everything would be getting closer toward us until everything eventually arrives at one spot. Therefore, that's how everything began. It all started from one spot and moved outwards. So again, this is the fundamental idea behind the Big Bang model. Now, of course, as a theory of cosmic origins, it has a lot of things to explain. It literally has to explain everything in the universe. And there's been a lot of work done on that. The Big Bang model itself at least the current version of it, can produce primarily hydrogen gas in the beginning of it. According to the Big Bang model, the early universe was roughly 3/4 hydrogen, roughly 1/4 helium, a little bit of lithium, and maybe a scrap of beryllium, but nothing else. The Big Bang can't make anything else. Of course, there's a lot of other stuff, a lot of other elements that we have to explain. Well, scientists have worked on this and have constructed models for how all this other stuff was constructed in the centers of stars, and in some cases in supernova explosions and some other means. My point is that we are now told that we have a comprehensive model explaining where all of this came from. The Big Bang made primarily hydrogen and helium, like I mentioned. Everything else came along later in what is claimed to be a good model. Now, the third major element of the Big Bang is a prediction that was made. A while ago, it was realized that if the Big Bang were true, we would see something in the sky that's called the cosmic microwave background. Basically, looking out into space, we should see a slight temperature in all directions. Now, obviously, if you're looking at a star or a galaxy, you're looking at something hot. But even looking into cold space, space itself should be bathed in a very low level of radiation. This was predicted and then found. So in the early 1960s, the discovery of this was really the crowning glory of the Big Bang model. This is the one that really discredited the other cosmologies that were its rival at the time, and the Big Bang has pretty much been the predominant model among secular cosmologists since then. By the way, if I use the word cosmologist in my presentation here, I'm referring to secular cosmologists, just to save some time. There are creationary cosmologists, but when I mention them, I will say so specifically, just for clarity. So those are the three fundamental pillars, really, of the Big Bang model. Redshifts, indicating that everything is moving away from us, therefore run the movie backwards and it all would have been in the same place. And then explaining where all the elements came from, and then a successful prediction of the microwave background. So this is primarily why the Big Bang is viewed as being good science today, because not only could it explain data that were already known, it also made a successful prediction. However, there's more to the story than this. My computer's acting a little wonky. So this is why it's thought to be good science. However, it's not quite as airtight as what is commonly presented. First of all, there are other explanations for the data that we see. For example, I mentioned redshifts. This is the slide I mentioned earlier that should have been in a different spot, but my computer decided not to show it. When something is moving away from you, you see redshifted light. When it moves towards you, the light is blue shifted. There are other explanations for cosmic redshifts. The Big Bang model is not the only model that can explain these things. Similar with element abundances and the microwave background and so on. So that doesn't make the Big Bang a bad model, but it does mean it's not the only exclusive model that can explain what we see. Having said that, I've shared with you why, or the primary reasons why, the Big Bang is believed by many to be good science. Now let's talk about why it's actually bad science. Let's go through the model chronologically. Here's how it goes. In the beginning, there was nothing, and then it exploded. What exploded? Nothing exploded. And nothing did explode, because that's why there's everything here today to talk about nothing. Stephen Hawking explained how and why this all happened. He said, because there is a law such as gravity, the universe can and will create itself from nothing. Spontaneous creation is the reason why there is something rather than nothing. Why the universe exists, why we exist. He explained further, the laws of gravity and quantum theory allow universes to appear spontaneously from nothing. Notice the plural, universes. We'll talk more about that here shortly. Cosmologists like Professor Hawking frequently invoke the laws of physics to explain how the universe formed itself from nothing. But what is a law of physics? Is it capable of producing a universe? What does a law of physics look like? What does it feel like? What does it smell like? That's a stupid question, right? A law of physics is not a thing. A law of physics is actually a pattern, right? A law of physics is just that we have noticed a pattern of how the universe operates and formulated it, hopefully into a good mathematical equation that can be tested. A law of physics is not a thing. If it's not a thing, it can't create anything, because a pattern can create nothing. More to the point, the pattern did not exist before the universe itself did, right? Because without a universe to operate, there's no pattern under which to operate. Does that make sense? So a law of physics can't create anything because the law of physics doesn't exist until there's a universe to display such behavior. Well, so if the laws of physics then couldn't create a universe, then who did? Who done it? Well, a more practical thing to say would be that various forces recognized by physics maybe did this. Now, physics recognizes 4 fundamental forces. I've listed them for you here. But according to the Big Bang model, when did these forces form? Before the Big Bang or after the Big Bang? And the answer is after. So if they didn't exist till after the Big Bang, could they have caused the Big Bang in the first place? Could the universe have created itself through these forces? Well, something can't create itself. Now we're running into philosophical problems, because in order to create something, it must first exist. For self-creation to be true, something must exist before it existed, which is obvious nonsense. And how do you go from nothing to everything anyway? In the beginning there was nothing, and then today there's everything. Well, we're told that nothing did it, but nothing can create nothing. Nothing can do nothing. From nothing, nothing comes. Right? R.C. Sproul once said, if there was once ever nothing, there could never be anything. And I like the way Dr. Phil Fernandez put it. He said, you can't tell me that nothing made everything. I know too much about nothing. So, now some people say, well, even if you wait long enough, even that which is extremely improbable will eventually occur. But that doesn't work either, because time itself didn't start until the Big Bang occurred. So there's no time to wait. Nor was there a place to wait, right? Because there was no space. Going on to specifics now. The Big Bang model made primarily hydrogen. Now, hydrogen is a very interesting gas. It has a lot of useful properties. Among other things, we can make airships and such because it floats. But think about how amazing hydrogen must be if you're a cosmologist. If you're a cosmologist, you believe hydrogen is an odorless, tasteless gas that, when given enough time, turns into people. Right? Isn't that the logical implication? Because if in the beginning there was only hydrogen and a little helium to mix in with it, and then here we are, that's what must have happened. Not only that, hydrogen wrote the works of Bach, Mozart, and Beethoven. Hydrogen wrote every work of literature, Shakespeare, Pilgrim's Progress. Hydrogen painted the Mona Lisa. Hydrogen does everything. Does that make sense? Does this conform to what we know about how the world works? Back when I was an engineer, I used to wonder sometimes, maybe this reflects being overly geeky, but I would go home at the end of a day and be very tired, having worked all day, and I would think, there's no physical representation of the work I just did. I mean, I'm tired, I did something. I concentrated hard all day. But a carpenter can look at the house and say, I did that. Or other people can say, I built this. I would write software all day, and what was physically different in the world? Well, the only thing that changed was different magnetic patterns on a computer hard disk somewhere. That's the only thing that changed in the physical universe. Yet I had created something. I had created software. Software is non-material information. But the Big Bang, strictly interpreted, is a materialistic worldview. There can be nothing non-material within a materialistic worldview. So information and other non-material things, like conceptual items, truth, justice, beauty, love, those things have no place within a Big Bang universe. There's also some very basic physics that are violated by the Big Bang model. Now, probably the most fundamental principle in physics is called the law of conservation of energy, law of conservation of mass energy, to be more specific. And that's saying that energy and matter can't be created or destroyed. You've probably heard of E equals mc squared. This is a famous formulation of this. E stands for energy, m is mass, and then c is the speed of light, which is a very large number. So if you remember your algebra, that means that a little bit of mass equals a whole bunch of energy. Now, we can convert things on either side of that equal sign. We can convert matter to energy, for example. The most efficient way we know to do that is a nuclear bomb. A little bit of stuff releases a whole bunch of energy. We can go the opposite direction, by the way. We can take a whole bunch of energy and make a little bit of stuff. We do that in particle accelerators. You get little pieces of atoms whizzing around fast enough, smash them together. More particles come out of the collision than went in. But we're not creating matter. We're just converting energy to matter. And as I said, you can go the opposite direction as well. Again, probably the most fundamental principle in physics. If you take physics in high school or college, practically every problem you solve, the first thing you do is assume energy and mass are conserved. Then you write the equation that reflects that, and then you solve it, and hopefully you did it correctly, and you get an A. But the rest of the world reflects the truth of this. That's why we need to eat food. Because your body can't create energy, it has to get it from an external source. You need to pump gas in your car, same reason. Because your car needs to take the mass, convert it into energy in order to provide kinetic energy, which is motion, and so on. If you've ever gone on a diet, you're relying on this principle being true. You're relying on your body's inability to create energy. You want to use up stored energy that you've unfortunately accumulated over the years. But the Big Bang violates this principle in the largest way possible. On a universal scale, literally. I mean, we can't violate this on a workbench in the laboratory, but Big Bangers tell us the entire universe popped into existence out of nothing. That all this matter and energy, poof, there it was. Now, a cosmologist, if you were to point this out to him, would just smile patronizingly and says, well, you don't understand the beauty of the Big Bang model, because there's a solution to this. Yes, it's true that nothing made everything, but everything is really nothing. Therefore, it's not a problem that nothing made everything, because nothing really made nothing. See how easy that is? When they say this, they're reflecting a common practice in cosmology, which is to model the universe in such a way that you take all of the stuff, stars, planets, galaxies, and so on, and energy that's within it, and you add that up into a number. Then you model the universe in such a way that all of its gravitational potential energy is a negative number, and you can do that in such a way that the two numbers are the same. So if you get a positive number and a negative number that's the same, add them together, what do you get? 0. So they say that the universe actually is nothing. That therefore the Big Bang could create nothing from nothing and not violate the law of conservation of energy. This is sometimes funnily referred to as the free lunch model. You may have heard the saying in economics, there's no such thing as a free lunch. Well, some people have said the universe is the ultimate free lunch because you get the whole universe for nothing, because it is nothing. Well, you can say that in your textbook if you want to, but in the real world, that line of reasoning doesn't work. Here's just one example. When I was a teenager, I was very much interested in audio, and I used to design and build speaker systems as a hobby, and then did a little bit of the work professionally as well afterward. I once worked on a project where the power supply that powered the speaker system was that part of the circuit, its whole job was to produce 2 voltages. There's 2 wires coming out of the thing that the rest of this speaker would use. And this wire produced plus 40 volts. This one produced minus 40 volts. And if minus voltage sounds weird, don't worry about it. It just means it's 40 volts below ground. So plus 40 volts here, minus 40 volts here. I could argue that this circuit on a net basis produced 0 volts, right? Same logic as what we just saw a moment ago. Nevertheless, when I unplugged that thing from the wall, it stopped working. Why is that? Well, because in the real world, you can't spontaneously diverge into positive and negative energy that counterbalance without expending energy to do that, which is what is necessary. That's why the speaker doesn't work unless you got it plugged in, drawing power from the power company, etc. You understand my point here? It's one thing to say that, okay, well, there's positive and negative energy and they cancel. Well, yeah, but that doesn't happen by itself. In the case of the speaker system, an intelligent designer had to build a system capable of doing that, and then you had to expend energy in order to make that happen. So now we're also running into thermodynamics and the fact that energy has to be expended for work to be done. So in trying to evade the first law of thermodynamics, conservation of mass energy, now they're running afoul of the second law, which is probably, as is said by many, the second most fundamental law in physics. So either way, you're violating fundamental physics, regardless of how you do this. These are not the exclusive problems with this model. There are others as well. Let's talk about a few. Early on, it was realized that one of the implications of the Big Bang is that there should be particles that are magnetic but only have one pole. So not north and south on the same thing, but only one. The problem is we don't see any particles like this in the world around us. The Big Bang, however, Big Bang model said that there should be plenty. So this was a serious problem for the Big Bang. It made a prediction that did not match the universe. There's also something called the horizon problem, where in measuring the temperature as represented by the microwave background that was discovered, the map turned out to be too smooth. There are parts on opposite sides of the universe that appeared to be very close to the same temperature, even though under the Big Bang model they couldn't have equalized temperature across those two locations. And I won't discuss that in detail because too much detail. For now, we'll just say this is acknowledged to be a serious problem for the Big Bang. There's also something called the flatness problem. Cosmologists model the geometry of space, and what that means we'll just set aside. We'll just acknowledge that that's what they do. And they were arguing over whether space would be this shape or this shape. I should say universe rather than space. But what surprised everybody was it turned out to be flat, which is near impossible in the standard Big Bang model. The Big Bang model should have gone way this direction or way that direction. It couldn't have stayed in the middle, but that's apparently what it did under their way of interpreting the universe. Around 1980, a cosmologist named Alan Guth found a solution to all three of those last problems. It's called inflation. What is inflation? Well, inflation is the idea that early on in the history of the universe, that tiny speck of brand new universe suddenly started inflating at a very rapid speed, much higher than the speed of light. And why it did that, well, we don't really know that. It was done by a particle called the inflaton. Well, what is the inflaton? You ever seen one? No. Where does it fit in the model? Well, it doesn't. But it must exist because otherwise those three fatal problems for the Big Bang remain. And this solves the three problems, therefore it must be true. Once you start inflation, how do you stop it? Well, we don't know that either. The universe isn't inflating today, so it must have stopped, but the model says once it starts, it doesn't stop. As an article in Astronomy magazine pointed out, as to what drove inflation, nobody knows. Physicists have suggested a long list of models to describe the inflating universe, but most of the proposed solutions are mathematical conveniences with no particular physical basis. All the theories of inflation amount to proof that we don't have one good theory yet. So is inflation a good scientific hypothesis, or is it a Band-Aid? A hand-waving saying, well, this must have happened and done such and such because it solves big problems for us, even though the such and such itself doesn't have a good basis. Moving on, other problems have popped up interpreting the universe under a secular interpretation, one of which is rotation curves. We can measure the velocity of stars as they orbit the centers of their galaxies, and physics makes certain predictions about how fast they should be going depending on how far they are away from the center. It turns out that the ones at the edges of galaxies, for the most part, are moving too quickly. Now, there's several explanations for this. The most popular one by far today among secular cosmologists is called dark matter. It turns out that you can explain these speeds if there was a big halo of mass outside here. That changes the way the dynamics work and changes the velocities. So therefore, there must be actually a lot of stuff out here that's doing that. Well, what is that stuff? It's dark matter. We don't see anything there. Well, that's because it's invisible. What do you mean invisible? We don't know of any matter that would do that. Actually, I should qualify that statement. There are solutions to this that are available, but the secular community rejects them, and I'll talk about this later. For now, dark matter is by far among secular cosmologists the predominant view that there must be all this extra stuff to explain these particular issues, even though we don't see anything. Now, they have subsequently discovered that some of the conventional solutions they thought they had for what dark matter might be don't work. So now the search is onward for exotic new forms of matter that don't produce light. I mean, they don't produce radiation of any kind. No X-rays, no light, no radio waves, whatever. The only effect it has with everything else is gravity. However, particle physics doesn't have anything like this. And even some secular cosmologists are uncomfortable here. This guy said, it's an embarrassment that the dominant forms of matter in the universe are hypothetical. So when you look in the sky, you see stars, planets, galaxies. That's normal matter. Cosmologists are now believing that there's a lot more dark matter than there is normal matter. And dark matter, again, is this hypothetical new form of matter that we don't know of. Moving onward from there. In the late 90s, it was discovered that some very far objects are displaying redshifts that are not consistent with Big Bang predictions. When interpreted under the Big Bang model, it appears that the universe's expansion is accelerating. Well, what could be doing that? Well, that's called dark energy. As Astronomy Magazine explained, to get enough oomph, that's a technical cosmological term, to drive the present acceleration of the universe, dark energy must make up about 73% of the total density of the universe. Now, basically, dark energy is anti-gravity. It's pushing against the gravitational attraction that all these various objects would otherwise have for each other and accelerating the expansion of the universe. But the biggest problem with this idea is that no one has any idea what dark energy is. So far, all we've been able to do is to name it. The nature of the dark energy that's causing the expansion of the universe to accelerate is now perhaps the most profound mystery in cosmology and astrophysics, and it may remain forever so. So let's take a brief state of the universe status. Here's what present cosmology tells us is true. 4% of the universe is normal matter, planets, stars, galaxies. That's everything we see in space. Almost a quarter of the universe is dark matter, which is completely unknown to physics. 3/4 of the universe's mass energy is dark energy, this mysterious anti-gravity, that's again completely unknown to physics. Now, the Big Bang model is supposed to explain everything. It's the theory of the origin of the universe, right? Now, if your theory of everything only explains 4% of everything, do you really have a theory of everything? I would say no. Yet it's still presented to us as a successful model. Moving onwards from here, there's something called the fine-tuning problem. There's actually a lot of different aspects to this that we won't have time to discuss. The universe, it turns out, is a very unlikely place for us to be. It's been compared to the difficulty of taking a sharpened pencil and balancing on its tip for 14 billion years all by itself. As people have dug into the Big Bang model and its implications and predictions, you see people making comments like this. Sir Fred Hoyle, no friend of creationists by any stretch of the imagination, he says some super-calculating intellect must have designed the properties of the carbon atom. Otherwise, the chance of my finding such an atom through the blind forces of nature would be utterly minuscule. A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics, as well as chemistry and biology, and that there's no blind forces worth speaking about. This astrobiological paper. There's now broad agreement among physicists and cosmologists that the universe is in several respects fine-tuned for life. It is fine-tuned for the essential building blocks and environments that life requires. Freeman Dyson said, "The more I examine the universe and the details of its architecture, the more evidence I find that the universe in some sense must have known we were coming." Among all the different ways that microstates of the universe can arrange themselves, only an incredibly tiny fraction correspond to a smooth configuration of ultra-dense dark energy packed into a tiny volume. That's a big phrase, but he's basically trying to describe what the Big Bang model requires. The conditions necessary for inflation to begin are extremely specialized and therefore describe a very low entropy configuration. If you were to choose configurations of the universe randomly, you would be highly unlikely to hit on the right conditions to start inflation. Being a little more specific about how fine-tuned we're talking about, a change of as little as 0.5% in the strength of the strong nuclear force or 4% in the electric force would destroy either nearly all carbon or all oxygen at every star, and hence the possibility of all life as we know it. Change those rules of our universe just a bit and the conditions for our existence disappear. Most of the fundamental constants appearing in our theories appear fine-tuned. If they were altered by only modest amounts, the universe would be qualitatively different and in many cases unsuitable for the development of life. For example, if protons were 0.2% heavier, they would decay into neutrons, destabilizing atoms. And since we're made of atoms, that would be a bad thing, in case that wasn't obvious. The emergence of the complex structures capable of supporting intelligent observers seems to be very fragile. The laws of nature form a system that is extremely fine-tuned. What can we make of these coincidences? Our universe and its laws appear to have a design that's both tailor-made to support us and, if we are to exist, leaves little room for alteration. That is not easily explained. It raises the natural question of why it is that way. Now, full disclosure, some of the things they're talking about are only applicable in a Big Bang cosmology. They're talking about if such and such was even slightly different, then planets could never have evolved, and so we wouldn't be here. Well, that's true. Since we don't accept the Big Bang model, that's not necessarily a design feature from our perspective. But from their perspective, it's a major problem that a lot of these constants are like this. This has been, add all this up, and some people have calculated that the chances of the universe looking the way it does are 1 out of 10 to the 60th power. So that's a 1 with 60 zeros after it. And as an illustration of how unlikely that is, Paul Davies said, suppose you wanted to fire a bullet at a 1-inch target on the other side of the observable universe, 20 billion light years away. Your aim would have to be accurate to that same part in 10 to the 60th. Since he said this, other people have realized it's actually a worse problem, and the number is now up to 10 to the 120th. Our universe appears surprisingly fine-tuned for life in the sense that if you tweaked many of our constants of nature by just a tiny amount, life as we know it would be impossible. Some of the fine-tuning appears extreme enough to be quite embarrassing. For example, we need to tune the dark energy to about 123 decimal places to make habitable galaxies. This is what 1 to the 120th power looks like. So 1 out of that number is the chances that the universe we see could have formed at random. Professor Susskind, again, no friend of creationists, has said this is a cataclysm for physicists. And the only way that we know how to make sense of it is through the reviled and despised anthropic principle. The anthropic principle is the idea that the universe must be suitable for us. And you can tell what he thinks of it by the adjectives he just used, right? Secular cosmologists do not like the implications that the universe appears to be designed because what does that imply? A designer. So what is their answer to this? Do they have a solution? Well, no. They actually have 10 to the 500 solutions. That's a 1 with 500 zeros after it. What do I mean by that? Well, this comes from something called string theory. String theory is the idea that the subatomic particles that we're familiar with aren't actually particles. They're actually little strings. So they're not 3-dimensional particles. They're actually 10-dimensional strings. Well, then why do they look like 3-dimensional particles? Because the other 7 dimensions are rolled up so small we can't see them. Now, this is claimed to be an explanation for lots of things in physics. Without delving into details, I'll just point out that string theory, unlike its name, is not a single theory, and it's not a single equation. It's actually a set of equations without a unique solution. There are actually 10 to the 500 possible solutions for string theory. So which one is correct? Well, most people today are saying all of them are. Each equation represents an actual universe somewhere with different laws of physics, represented by that particular set of constants and solutions to the equations. So let me repeat that. 10 to the 500 universes. Now, right out of the gate, we might be scratching our heads. The universe is everything there is, so how can there be more than one of that? Well, because they've redefined the word universe to mean that which we can observe. Not necessarily that which we can observe today, but that which we could ever potentially observe, even with the best possible equipment. So we do not live in a unique universe. We live in one of 10 to the 500 universes, which can have infinite combinations of different, I shouldn't say infinite, myriad combinations of laws of physics. Now, that sounds like a pretty goofy idea. What's driving all of this? Well, because without string theory, we would be left with no other rational explanation for the illusion of a designed universe. See, the idea is, they admit our universe is extremely unlikely. 1 out of 10 to the 120th power, right? I mean, that's impossible, basically. But if you have 10 to the 500 universes to pick from, there's going to be one very unlikely in there somewhere, and we just happen to be in that one. Even this, though, isn't sufficient for some people. So many cosmologists are now teaching there is actually an infinite number of universes. And this comes actually from our good friend inflation. Inflation, when it was first proposed, was thought to be a fairly simple process. As subsequent work has been done, they find out that no, it's not simple. Inflation did not stop all at once. It would break down, to make a long story short, and you would have eternal inflation going once it started. It can't stop. As this quote says, once inflation starts, it's nearly impossible to stop. An infinite multiverse of universes is formed. Multiverse equals multiple universes. Even in the tiny pre-inflation cosmos, quantum fluctuations ensured that the inflaton field, remember that particle that nobody actually knows what it is, had different energies in different places, a bit like a mountain having many balls balanced precariously at different heights. As each ball starts rolling, it kicks off the inflation of a different region of space, which races away from the others at speeds above that of light. Blah, blah, blah. Key point. an infinite multiverse of universes is predicted by inflation. Now, this has some pretty weird ramifications, as this paper began with. Is there another copy of you reading this article, deciding to put it aside without finishing the sentence while you are reading on? A person living on a planet called Earth, with misty mountains, fertile fields, and sprawling cities, in a solar system with 8 other planets. This paper was published right before Pluto got demoted. The life of this person has been identical to yours in every respect until now. That is, when your decision to read on signals that your two lives are diverging. You probably find this idea strange and implausible, yet it looks like we'll just have to live with it, since the simplest and most popular cosmological model today predicts that this person actually exists in a galaxy about 10 to the 10 to the 29th meters from here. The software doesn't allow me to do 2 superscripts, but this is 10 to the power of 10 to the 29th. So this person is very far away from you, but with an infinite number of universes to choose from, there's going to be one identical to this one, with just 1 or 2 smaller respects. There's a universe out there just like this one where someone with your name and looking like you in your history had something different for breakfast this morning. There's a universe out there where the South won the Civil War. There's a universe out there where fill in the blank. Anything you can think of. Because there's an infinite number to choose from, so everything is going to be there somewhere. This does not even assume speculative modern physics, merely that space is infinite and rather uniformly filled with matter, as indicated by recent astronomical observations. Your alter ego is simply a prediction of the so-called concordance model of cosmology, which agrees with all current observational evidence, if you make certain assumptions, and is used as the basis for most calculations and simulations presented at cosmology conferences. If space is infinite and the distribution of matter is sufficiently uniform, then even the most unlikely events must take place somewhere. In particular, there are infinitely many other inhabited planets, including not just one, but infinitely many, with people with the same appearance, name, and memories as you. Indeed, there are infinitely many other regions the size of our observable universe where every possible cosmic history is played out. This is mainstream. Let's focus on this one sentence. Even the most unlikely events must take place somewhere. We'll come back to that. And again, remember that some versions of this say that different laws of physics can apply in different universes. Now, I just told you this is mainstream, and you still might find this kind of hard to believe because this whole idea sounds pretty weird. But no, this is mainstream. I mean, lots of books are coming out on this. Article New Science has said, our most successful theories lead to the inescapable conclusion that our universe is just a speck in a vast sea of universes. The multiverse is not some kind of optional thing, like can you supersize or not, says this theoretical physicist. Our own cosmological history, he says, tells us that it's there and we need to deal with it. So if you find this idea too weird, well, you better just deal with it. Is this good science? By definition, all these other universes are unobservable by us. Again, even if we have better telescopes, best telescopes possible, can't do it because, for example, inflation, there's inflation going on faster than the speed of light, which prevents light ever traveling between the universes. Thus, we could never see, observe, measure these other universes whatsoever. So to invoke things that are outside of our observation doesn't sound like good science to me. Especially when the primary motive is, in this case, inflation, which is to rescue your theory from fatal observational problems. It interests me that something like inflation is presented as evidence for the inflationary Big Bang model, when inflation is where the actual data behind the inflation in the first place is data against the Big Bang model, if that makes sense. So we started out by saying, or by explaining why people claim the Big Bang is good science. Now we see that maybe it's actually not good science. There's a lot of bad science being invoked here. Now at the beginning of the talk, I said I would share a reason why the Big Bang is actually anti-science and makes science impossible. I'm not going to do that. I'm going to share 7 reasons why the Big Bang is anti-science. Number 1, it violates physics. We talked about that before. The most fundamental principles in physics are violated right out of the gate by the creation of the universe from nothing. Nothing doesn't create everything, and you can't make the excuse that everything creates nothing because that argument holds no water. Number 2, the Big Bang invalidates physics itself and laws thereof. What's the most basic thing you need in order to do physics? Now, you might think, let's see, laboratory equipment or more fundamentally math. No, the most fundamental thing you need to do physics is a universe where physics applies. Right? Think about the Big Bang model. There was no time before the Big Bang occurred. Therefore, there can be no cause for the Big Bang. And this is actually acknowledged. Yeah, I mean, that the Big Bang just happened. In fact, one guy said the universe is simply one of those things that happens from time to time. There can be no cause. There's no reason for the Big Bang. And actually, there's entire books being written on this saying that having no reason is perfectly justifiable. So if the universe itself popped into existence for no reason whatsoever, why would you expect it to act strictly according to laws of physics from that point on? Right? If the universe is founded in randomness, if it's essentially a random thing and came from randomness, then why are you going to disallow randomness from that point on? Well, in order to do science at all, though, you have to say it's not random, because you have to assume that there is patterns of behavior that we can discover with enough inquiry. Now, as Christians, we can make assumptions that make science possible. We believe in a God of order. I mean, the Lord upholds the universe through the power of His Word, right? Scripture says that day and night, summer and winter will not cease, saith the Lord, etc. There's lots of scriptures you can point to that says God created the creation to operate according to certain ways, and it would do so regularly. Now, He can intervene in the form of a miracle every now and then if He chooses to. That's His privilege and right, certainly. But other than that, we as Christians can assume that the universe has patterns of behavior that will be adhered to by the creation, which is why there's so many famous scientists who were Christians. Isaac Newton, Faraday, Maxwell, I mean, all these guys, giants. They thought they were thinking God's thoughts after Him by doing science. And they viewed it as their joy and privilege to try to discover patterns in what He had done. Big Bangers don't have that capability because their universe came from nothing for no reason whatsoever. How then can they assume that it's going to operate according to patterns from that point on? Now, if you point this out to someone, you might get the rebuttal, but we do observe patterns, and so we can assume that they're there. Well, yes, I know there's patterns. That's because a God of order created everything. Consistent with my worldview, not consistent with yours. But actually, that excuse doesn't work for them anyway, because in order to apply patterns, they have to use something called induction. Induction is a form of logical reasoning, and the Big Bang and its implications nullify that. What do I mean? Who believes that copper conducts electricity? Some people aren't so sure where I'm going with this. Well, the fact that you're here watching this presentation means that it does, because there's copper in this wires, and the electricity is powering my laptop and powering this thing and the lights above us and so on. Do we therefore know that all copper conducts electricity? I mean, there's copper on other planets, let's say. Do we know it conducts electricity? We've never tested it. We've never been there to get any. Well, it seems reasonable that it does, right? Because we've tested a lot of copper here on Earth, and so it seems that applying inductive reasoning, we can apply that pattern elsewhere. We also do this through time. We assume that copper will work tomorrow as well as it works today. I mean, is anybody worried that gravity is going to turn off at 6:35 tonight? No, because it's always worked. Well, this is inductive reasoning, where induction acknowledges that we can't possibly measure all copper in the universe simultaneously to make sure it all conducts electricity. Nor can we test it in the future because it's not the future yet. So induction says I can measure a small pattern and then extend that outward under certain conditions. Now, this is actually a problem for an atheist who wants to do science. And we're getting a little bit off topic here, but I think this is really interesting. Over 200 years ago, an atheist philosopher named David Hume thought about inductive reasoning and realized that as an atheist, he couldn't use it because he couldn't prove it to be true under his worldview. Now, he acknowledged that he had to use it in order to survive. He said, because I have no way of knowing that the bread that was nutritious for breakfast, might be poisoned by the time lunchtime comes around. I don't know that the sun's going to rise tomorrow morning. He actually said this. He said it always has, but in order to say that it will continue to do so, I have to use induction. And again, as an atheist, he realized there's no foundation for induction. Now, again, as Christians, we can use induction because we have a God of order who created the universe in such a way. Where am I going with all this? Well, let's say I came to you and I said, you know, I have this die, and it's really neat. I rolled it a bunch of times, and here are some of the results I got. I rolled it 6 times, and I got the numbers 1 through 6 in order. I rolled it 6 more times. I got the numbers 1 through 6. I rolled it 4 times. I got 1 through 4. And on my 5th roll, what do you think I got? Who thinks the answer is 5? Everybody's nervous now where I'm going with this one. Well, no, the answer wasn't 5. The answer was, let's say, 2. And you say, well, how can that be? It had this pattern. But there's something I didn't tell you. I rolled the die 2 million times. And then I found the sequence within it. So I didn't lie to you. I did actually roll it in this sequence. But that was a small sample of a much larger random sequence. So are we surprised now that somewhere within that randomness there was an apparent pattern of order? Not surprising, right? Now extend this to the multiverse idea. We observe what appears to be patterns of behavior in the universe around us. And we codify that in the laws of physics. How do we know that our limited observation time, when compared to the vastness of the universe and now the even vaster multiverse, how do we know that our observed, what appear to be strict patterns, aren't just examples of this? What appears to be order is actually an illusion because it's taken from a much larger pattern of disorder where there's nothing going on but randomness. Do you see the point I'm making here? That we base all of our science on observations we have made in our limited human history doing science. If the multiverse in particular is true, we have no way of knowing that what appears to have been order the whole time wasn't just actually an illusion. Because there's this much larger sample of reality that we're not looking at. Does that make sense? That's maybe a little too abstract. Along with induction, the Big Bang model also nullifies what's called abduction. And no, I'm not talking about kidnapping. Abduction is a form of reasoning also sometimes called the inference to the best explanation. And we use this all the time. For example, let's say you're at home and there's nobody else home but your dog. It's just you and the dog in the house. And you're hungry, so you go in the kitchen, you make a sandwich, and before you can eat the sandwich, though, you haven't even taken a bite yet, the phone rings in the other room. So you put the sandwich down, you go into the phone, you come back in the room, and this is what you see. Now, who gets in trouble? Do you call up your neighbor and yell at him, you got a lot of nerve sneaking into my kitchen, taking a bite from my sandwich, and sneaking out again before I could catch you? No, that's not the best explanation. So who gets in trouble? The dog, right? You can't prove it was the dog who did it, short of, cutting the dog open, examining its stomach contents, or whatever. But the best explanation is the dog done it, right? And our society is based on this principle being true, that we can use the best explanation. For example, a criminal standing before a judge. Judge says, you've heard the evidence against you. What do you have to say for yourself before the court passes judgment? The accused says, well, Your Honor, here's how it is. I know there appears to be a lot of evidence against me, but I can explain. See, I know that what appeared to be my footprint was found at the scene of the crime. But you see, the wind and the rain eroded the soil in such a way that it just happens to look like my footprint. And I know I was found with a bag of stuff that looked like all the goods that were stolen, but I just happen to own identical articles of each item that was taken from that person's house. And I know someone else claimed to have seen me at the scene of the crime, but you see, genetics tells us that there's someone else in the world that looks a lot like each of us. And so that person just happened to be at that location where I was somewhere else. Because, and I know this is all very unlikely, Your Honor. I know it sounds contrived and far-fetched, but you see, we live in a multiverse. And in a multiverse, even the most unlikely events must take place somewhere. Now, is the judge going to accept this form of reasoning? No, that guy's going to jail. We reject this form of reasoning everywhere else in life. Why do we accept it when it comes to a cosmologist? Number 5, Big Bang model taken to its conclusions destroys predictability, which is an essential part of science. For example, Stephen Hawking has written, a bottom-up approach to cosmology. By bottom-up, he means trying to describe the early universe mathematically and then following the equations forward to see what predictions are made and then seeing if the universe matches those predictions. It either requires one to postulate an initial state of the universe that's carefully fine-tuned, as if by an outside agency, i.e. God, which he does not want, or it requires one to invoke the notion of eternal inflation, which prevents one from predicting what a typical observer would see, because eternal inflation produces all possible effects. As this article, New Scientist, pointed out, I quoted the first paragraph earlier, once inflation starts, it's impossible to stop. an infinite multiverse is formed, this is not good news for our hopes of cosmic enlightenment. In a single universe, an underlying theory of physics might offer a prediction for how flat the universe should be, say, or for the value of dark energy, the mysterious entity that seems to be driving an accelerated expansion of the universe. Astronomers could then go out and test that prediction against observations. But that's not possible in an infinite multiverse. There are no definite predictions, only probabilities. Every conceivable value of dark energy or anything else will exist an infinite number of times among the infinite number of universes. And any universal theory of physics valid throughout the multiverse must reproduce all of those values. That makes the odds of observing any particular value infinity divided by infinity, which is a nonsense that mathematicians call undefined. Basically, the Big Bang model has wound up in a spot where you can't make mathematical predictions about what the universe would be because the model predicts literally everything. As an illustration of this, let's say I told you I have a new theory called arbitrary gravity. That when I drop an object, most of the time it'll fall, but once in a while it won't. Sometimes it'll hover, sometimes it'll go up or down in any particular direction. And I say, this is such a great theory, it explains everything. Watch, and then I demonstrate by dropping things. I say, look, it's consistent with my theory. You say, well, yeah, but everything would be consistent with your theory. Well, yeah, that's because it has great explanatory power. It's consistent with all the observations. Well, how do you disprove such an idea? Obviously, you can't, right? Because there's no possible experiment that would show if this theory is true or false. A theory that predicts everything actually predicts nothing. It's worthless as a scientific hypothesis. But that's ultimately what the multiverse does. You can't say, let's examine the Big Bang model and see what predictions it makes and see if those predictions are verified by experiment, because it predicts everything. Therefore, it explains nothing. Reason number 6, the Big Bang is self-contradictory. I mentioned earlier that all the various universes other than our own are by definition unobservable. We can never see them regardless of how good our equipment is. So if something is unobservable, it's outside of the natural world, it's outside of nature. What word do we use to describe something outside of nature? Supernatural. And if you remember, the Big Bang theory explicitly rejects anything supernatural from the very beginning, because naturalism is the only allowed explanation, right? So here we have the Big Bang, or at least, not the Big Bang model specifically necessarily, but cosmology in general today, rejecting biblical creation because it's supernatural, and we can't allow anything supernatural to come in when embracing and ultimately requiring the supernatural explanation of its own. And even on the secular side, some people are unhappy with this. These multiverse theories all share the same fundamental defect. They can be neither confirmed nor falsified. Hence, they don't deserve to be called scientific. Multiverse theories aren't theories. They're science fictions, theologies, works of the imagination unconstrained by evidence. My own moral concerns about the multiverse have more to do with worry that pseudoscience is being heavily promoted to the public. If a wrong idea is promoted for enough years, it gets into the textbooks. Well, we wouldn't know anything about that, would we? And becomes part of the conventional wisdom about how the world works. This process is now well underway with multiverse pseudoscience. Take this idea to its logical conclusion, or illogical conclusion, I guess, and you wind up in some really weird places. And the fruit of a theory will tell you how good the foundations are. As an example, this is a serious scientific paper, the beginnings of it, published in the Quarterly Journal of the Royal Astronomical Society, a very prestigious organization. It is proposed that our universe was created by life of superior intelligence existing in another physical universe. Intelligent beings, perhaps our own descendants in the far future, might possess not only the knowledge to design, but also the technology to build universes. This forms the basis of a theory of natural selection of universes. Boy, Darwin applies everywhere, doesn't he? Intelligent life in parent universes creates offspring universes. And in the offspring universes fit for habitation, new life evolves to a high level of intelligence and creates further universes. Universes unfit for habitation lack intelligent life and cannot reproduce. So here's natural selection, right? The fit survive and the unfit don't. This natural selection process explains why the constants of physics have their observed, finely tuned values and might even help us to understand why our universe is comprehensible to the human mind. Does that make sense to anybody? Is this type of thinking good science? Here's another paper from Dr. Ronald Breslow, very accomplished scientist, long list of awards, member of multiple academies, lots of publications. He wrote a paper here recently where he was describing how he's trying to solve the chirality problem, which describes how left-handed and right-handed molecules could sort themselves out so life can form. And in discussing how life might have been seeded on other planets, at the end of his paper, he mused a little bit on the fact that, well, you know, since we know evolution happened here, then evolution should happen elsewhere too, and it should really proceed in similar fashion. So some of those other planets probably have dinosaurs on them. Now, here on this planet, though, dinosaurs only are not around today because they got wiped out by a freak asteroid collision. And what if dinosaurs on other planets hadn't been wiped out by freak asteroids? Well, they would have evolved further. Eventually, maybe, you get this. Such life forms could well be advanced versions of dinosaurs if mammals did not have the good fortune to have the dinosaurs wiped out by an asteroidal collision, as on Earth. We'd be better off not meeting them. Because there's nothing worse than doing space exploration and running into alien dinosaurs with better weapons than you have, right? But isn't this a logical implication? Now, he wasn't invoking the multiverse ideal specifically, but it's very consistent with this. Anything that's possible will happen somewhere. So yeah, dinosaurs with weapons. See, all this time you thought Calvin and Hobbes was a cartoon. It's actually a documentary, right? Tyrannosaurus flying F-14s. You can have some fun with this, too. If you're talking to an atheist who tells you, oh, the Big Bang shows that God's not necessary, there's no God, blah, blah, blah. Ask him if he believes in the full Big Bang theory and all its implications today, including the multiverse. And then say, well, you know, I want to change the subject for a minute. Do you agree with Richard Dawkins, where in his book, The God Delusion, he said there is almost certainly no God? Well, you're asking your atheist friend this. And if he's an atheist, you're probably going to say yes. Say, okay, well, let me rephrase that a little bit and see if you still agree. It is most unlikely that the God of the Bible exists. Do you agree with that statement, Mr. Atheist? And he'll say yes. Well, you know, in a multiverse, even the most unlikely events must take place somewhere. Therefore, the God of the Bible exists elsewhere in the universe, but that God of the Bible insists that there is no multiverse, there's only one universe, and that destroys all the rest. So the whole multiverse idea logically self-destructs, doesn't it? Reason number 7. The Big Bang is ultimately driven by ideology, not science. I told you earlier that the foundational discovery that started the whole thing was redshifted starlight. What I didn't tell you, though, is that there's actually 2 choices in how to interpret these data. Number 1 is that we appear to be at the center of an expanding universe where everything is moving away from us, because it would look this way from anywhere in the universe you happen to be, which is the option that Edwin Hubble chose. Option number 2 is that we appear to be at the center of an expanding universe because we are. That option he rejected. Why? He said that hypothesis cannot be disproved because both of those interpretations is consistent with what we see. But it is unwelcome, and it would be accepted only as a last resort. Therefore, we disregard this possibility and consider the alternative. Why is that? Because there's the unwelcome supposition of a favored location must be avoided at all costs. A favored position is intolerable because that would imply that we're special, and we don't want that. Therefore, to restore homogeneity and to escape the horror of a unique position, we make adjustments to the theory and so on. There seems to be no other escape. My point is, he was making a choice at the very beginning as to how to interpret this. And this is something that's usually not discussed in the Big Bang model. The observations support 2 ways of looking at things. The Big Bang model requires what's called the cosmological principle, which is there can be no special places in the universe, because that would imply that there's a God or something behind it all. And if there's no special places, then you have to interpret the redshifts in such a way that produces ultimately the Big Bang model. But this is not a scientific thing. You have to make the choice before you can apply any math, before you can apply any physics. As Stephen Hawking and his co-author admitted, we are not able to make cosmological models without some mixture of ideology. Scientific American. People need to be aware that there's a range of models that can explain the observations. For instance, I can construct you a spherically symmetrical universe with Earth as its center, and you cannot disprove it based on observations. You can only exclude it on philosophical grounds. In my view, there's absolutely nothing wrong with that. What I want to bring into the open is the fact that we are using philosophical criteria in choosing our models. A lot of cosmology tries to hide that. And the choice that is made at the very beginning over how you interpret these observations, that's what requires dark matter and some of its uses, dark energy, and a lot of these other band-aids that I told you about. These aren't necessary if you make a different choice at the beginning of the model. But because they reject that possibility because they don't want God to sneak in, then they wind up with all these other solutions that really smack of desperation. As this cosmologist said, if there's only one universe, you might have to have a fine-tuner. If you don't want God, you better have a multiverse. My time is running out, so normally I would review some of the scientific problems that we discussed at the Big Bang. I want to reiterate the point that I made last night. This is not a war of religion versus science as it's portrayed. It's not that there's science over there and we're religious over here. Is creation a faith-based view? Yes, absolutely. But so is the Big Bang. And the Big Bang, as I said, is self-contradictory. It claims to reject supernatural explanations while requiring them. It claims to embrace science while ultimately making science impossible. And it's based on a philosophical choice to reject any possibility of us having a special place in the universe. Now, for clarity, I'm not a geocentrist. I'm not saying the Earth is stationary and the sun goes around, etc. But the idea of our galaxy being somewhere close to the center of the cosmos, again, is consistent with the observations. Now, a brief note to people who try to use the Big Bang and they're apologetic, and unfortunately there's a lot of these. People are told, well, the science says that there was a Big Bang. It sounds reasonable because if stuff's moving away, then it must have all started from the same place in a Big Bang. So we should try to reconcile that with the Bible. And as Chris said this morning, what reconcile usually means is change what the Bible says. But our talk here this morning should be a good warning about this. Number one, the Big Bang is not good science, as we've seen. It violates most important laws of science and makes a scientific approach impossible if you really think about it. It's also built on an anti-theistic foundation, a rejection of the possibility that we could be at a special place in the cosmos. So building your theology on an anti-theistic assumption, of course, obviously is not a good thing to be doing. And lastly, if you're going to build your theology on the Big Bang, you're building it on shifting sands. A friend of mine likes to point out that all scientific theories have shelf lives, right? I mean, what is believed today might be thrown out on the garbage heap tomorrow. Scientific theories come and scientific theories go. If you change your interpretation of the Bible, then you're in quicksand. The Bible is our authority. It says, in the beginning God created the heavens and the earth. This is the Word of God. Now, it doesn't need me to say it's our authority. It has its own authority. But my point is, we should be basing our worldview, our foundation, our science on this, which does not change, versus the Big Bang, which is anti-science and probably will change. There are cosmologists who do not like where the Big Bang model currently is today. Not so much the multiverse thing, but a lot of people dislike the idea that there was a beginning. And there are cosmologists out there trying to build secular models that get away from that. There's a cyclic universe model, there's a neo-steady state model, there's others. There are people trying to eliminate a beginning of the universe from the secular model. Now, that hasn't caught on yet widely, but it might someday. And if you are basing your interpretation of Scripture on what the majority scientific opinion today happens to be, where are you going to be where that opinion changes to deny any kind of beginning to the universe? I think the answer to that would be clear. As Psalm 19 says, the heavens actually declare the glory of God, and the firmament shows his handiwork, so we should believe that, because indeed they do declare his glory. Briefly, on the book table in the back there's a couple of DVDs. If you like this perspective on astronomy, you can get more of it back there. What I shared this morning is not yet on a DVD form. Of course, you've just seen it live. The DVD is back there. I had some questions about this. Number one, which is this, goes through every planet in our solar system and a lot of their moons. Each planet in the solar system actually discredits the secular model of origins in a different way. Now, this is not the Big Bang model specifically, because even the other secular cosmologies have to explain planets also. But it is refuting the secular model for where all this stuff came from. It's a very fun study. There's 240 some odd photographs in that one. Volume 2 goes through stars and galaxies, shows the same thing. Take the secular model to its logical conclusion and see, can it explain what we see in the cosmos? And the answer is no. I also have a free email newsletter you're welcome to sign up for. I have a clipboard here if you want to give me your name, or you can go online. There's a sign-up box here, creationastronomy.com. And my time is done. I thank you for your attention.